The Bathypelagic zone is the largest contiguous ecosystem on Earth. It is also the darkest, the most highly pressurized, and the most fiercely resource-starved. Below 1,000 meters, the complete absence of downwelling solar light creates a severe biological constraint. The visual interaction hypothesis suggests that without light, the distance at which an animal can detect predator or prey drops to essentially zero. If you cannot see anything approaching, maintaining a high metabolism to support dense, evasive muscle tissue becomes a wasted investment. The environment selects against the mechanical systems that power most marine life. To survive the resulting caloric deficit, deep-sea vertebrates substitute solid musculature for highly watery, gelatinous tissues. It is a necessary physiological compromise to lower their base energy requirements. Within these extreme metabolic limits lies a paradox. The deep-sea anglerfishes, Ceratioidei, are the most species-rich fish taxon in the Bathypelagic realm. Surviving the void requires abandoning standard vertebrate locomotion. Success here depends on radical, energy-efficient morphological adaptations. We can see exactly how they achieved this dominance through the results of a comprehensive pelagic trawl survey conducted in the Gulf of Mexico following the Deepwater Horizon spill. The scope of the collected data is massive. Researchers cataloged 1,726 individual ceratioid specimens, spanning all 11 families within the suborder. The nets captured 3 drastically different life stages and morphotypes: massive adult females, dwarfed free-living adult males, and larvae. This chart plots the exact capture depths of those 1,726 specimens, from the surface down to 2,000 meters. The data reveals that their high species diversity is maintained by rigidly partitioning the water column into 4 distinct spatial distributions. The Gulf of Mexico dataset proves the Bathypelagic is a fiercely divided and highly structured habitat. This diagram models the foundational life cycle for ceratioid anglerfishes, ontogenic vertical migration. The cycle begins when fertilized eggs float upward from extreme depths to the ocean surface. This places larvae in the epipelagic zone, utilizing the sunlit upper 200 meters for rapid development. Physiologically, these larvae are adapted specifically for surface survival. They possess large fins and translucent bodies to aid in their development. Even at this early stage, intense morphological variation is apparent across different families, as seen in this elongated specimen with its distinct tail filaments. Returning to the model, a critical biological trigger occurs. Metamorphosis initiates a massive one-way descent back into the deep ocean. This ontogenetic descent permanently locks the adults into the high-pressure, lightless environment. Anglerfishes exploit the ocean's entire vertical column to completely separate the caloric demands of juvenile growth from adult reproduction. Plotting the Gulf of Mexico data maps exactly how this partitioning works. This is pattern 1, an epipelagic residence followed by a rapid ontogenetic descent. The primary biological representatives holding this specific distribution pattern are the larvae of the family Linephrynidae. Moving lower in the water column, we find pattern 2, a primarily mesopelagic occurrence, holding strictly between 200 and 1,000 meters. The dominant demographic occupying this midwater niche are the adult females of the family Ceratioidei. A Ceratioidei female, like this Cryptoceras cuisi, physically reflects its depth range. Its dark, globose body and specialized eyes are adapted for the twilight zone. Maintaining a mesopelagic residence provides these females first access to biological matter descending from the surface. By isolating pattern 1 larvae at the surface and pattern 2 females in the midwater, anglerfishes ensure that different generations do not compete for the exact same scarce calories. The next distribution defies strict depth boundaries. This is pattern 3, the spanner distribution. Spanner species, like Haplophryne mollis, traverse massive vertical distances. They ignore typical stratification limits and solar cycles to maximize their rare foraging opportunities. Finally, we reach pattern 4, a strictly bathypelagic residence, permanently locked well below the 1,000-meter line. The demographic makeup of this deepest zone is an anomaly. It is overwhelmingly dominated by free-living, dwarfed males. These males carry severe physiological deficits. Lacking lures and possessing underdeveloped alimentary canals, they are effectively starving from the moment of metamorphosis. They operate under a single evolutionary directive, utilizing massive olfactory organs and specialized retinas to locate a female before their energy reserves expire. The deepest, most extreme layer of the ocean is not a feeding territory. It serves primarily as a high-stakes, time-limited mating ground. When a millimeter-scale male successfully navigates the pattern 4 depths, he encounters a massive female, like this Melanocetus morai. To secure his survival, the male permanently locks onto the female using species-specific denticular jaws. Standard biology textbooks universally classify this relationship as sexual parasitism. That classification is a scientific misnomer. The strict immunological criteria for a parasite requires an interspecies interaction. A male attaching to a female of his own species does not qualify. The physical connection involves true vascular fusion. The male's circulatory system integrates seamlessly into the female's without triggering an immune response, demonstrating perfect physiological integration. The correct scientific classification is genetic chimerism, occurring when 2 distinct genetic lines merge into one functioning organism without immune rejection. This attachment is not a parasitic attack. It is an extreme evolutionary hack to guarantee reproduction in an environment where finding a mate twice is statistically impossible. Combining all 4 distributions from the Gulf of Mexico reveals the complete ecological model of the Bathypelagic anglerfish. It maps a complex interlodging system, exploiting the surface for rapid growth, the midwater for specialized feeding, and the absolute depths for chimerism. The metabolic economics are precise. Shedding muscle tissue and utilizing bioluminescent lures provided the exact energy budget necessary to power this vast vertical stratification. Early hypotheses assumed the deep ocean was sparsely populated and chaotic. This dataset proves the reality is highly structured. The Ceratioidei occupy the Bathypelagic through this multi-layered vertical partitioning, maximizing their chances in a void defined by scarcity. Dominating this lightless ecosystem requires extreme morphological specialization, embodied perfectly by the whip-nose anglerfish. The ceratioid anglerfish represents the absolute limits of vertebrate adaptation on Earth. The deepest, darkest, and most desolate place on the planet is actually its most strictly organized biological frontier.